Alright, today we're going to do the part 2 of Arenes. We have talked about the structure. Today we're talking mainly about is the reactions, the main mechanism is here, electrophilic substitution. I'll show you. The keyword today is this one, electrophilic substitution. Okay, and mechanisms. But before we go into that, I want to talk about certain other stability. Stability, how actually see in thermochemistry point of view. Now, you see, I told you that the benzene, there are two structures you can see here. This is called this one is called the resonance structure. Okay. This is called the resonance structure. Resonance. Okay. Just explain why, because all this is called the delocalized structure. Delocalized. Commonly referred to as Kerkuli. Kerkuli is the guy I told you, this ring structure, which means all in this structure here, all the bonds, the CH bond, the CC bond, are similar length. Okay. sp2 hybridization, hybrid, so they should be like this one here, a double bond here, double bond here, double bond here. See? So it should be double bond here, the double bond here. I'll put a red thing first. The double bonds here, right, should be stronger and shorter. It's found not true, but let's say we assume this is the structure. It's called a cyclohexatriene. Triene means three double bonds. Triene. Ene, of course, is the name for carbon, double bond carbon as well. Remember, this is your alkenes. So triene, hexa means 6, cycle means all round. Now, if we were to do, let me rub off this one first. This one here. Now, if we were to talk about double bonds here now, if there were one single double bond, it's called cyclohexene. Cyclohexene, right? Ene means double bond. Well, this is one B. You don't. Okay, this is 4-5. You use this normally in your experiment. You will use this because liquid here. This will colorize bromine very easily in the dark because of the double bond here. But this fellow here, benzene, or this guy here, will not decolorize bromine. It's very unreactive. Why? Now here you can actually see why. Okay. Now if you imagine there were three double bonds here, okay, in this fashion here. Now, if it's one double bond here and you hydrogenate it, very easily hydrogenate because it's very reactive. Remember, it's very reactive. Right? Addition reaction. And it will give you a cyclohexane. It's called cyclohexane, ANE. Because all of them are, well, single bond, sp3, sp3, or sp3. They found that the heat given up for one double bond is minus 118, which is exothermic. So if this were three double bonds, right, the heat, the hydrogenation would give up 3 times the one here. Okay, so if this is the structure and it's going to here, why is going down? Because it's negative. So they found that it's minus 354. And they actually, now this is a theoretical idea. Theoretical. Because we assume the here double bond, there are 3 double bonds here. But in reality, right? So we take this benzene and experiment. That means in reality, when you hydrogenate, you only get minus 205. You get the same product. See, the same product. The base here is the same. But if it is here is minus 354, and here the real one is 205, that means the structure of benzene is lower. And here it is lower energy. So now this difference in energy is called the resonance energy, or sometimes called the delocalized energy. Okay, so which means the benzene is more stable than the actual idea, the theoretical idea of 3 double bonds. That's why benzene, right? In reality, benzene does not undergo oxidation, which means that now if you remember your alkenes properly, double bond, right? Okay, this is a normal alkene. This can easily undergo addition reaction in form 5 with bromine, or even in your A2 in the dark. No need any energy. It will actually add on to give you your dibromo. This is very common. This is a test for your double bond. Okay, decolorize. Okay. Also, the other reaction which is common for double bonds is your reaction with KMnO4. Remember, this is what you have the equation here. The KMnO4, right, will be decolorized, acidified. The T is oxidized to give you your first part here, which is your diol. Okay, this will be decolorized. So two reactions KMnO4 is purple. Purple is decolorized, and of course your here reddish brown orange is decolorized. Now these two reactions are very common for alkenes if the double bond is fixed. But in your benzene, no reaction. No. Benzene, no reaction if it's benzene, yeah. So that's why we draw the delocalized version. So if it's Br2, no reaction. If it is KMnO4, also no reaction. All because it's being delocalized. It actually delocalized. Okay. Now let's go to so what kind of reaction has it got? Electrophilic substitution. Now you look at it carefully here. The syllabus tells you there are 4 or 5, 4. Okay? 4 reactions they will ask. 5 actually 5. Okay, let's see here. First, of course, is here. See, describe the chemistry of Arenes as exemplified by the following reaction of benzene and metabenzene. Now we look at metabenzene later, but look at benzene first. Okay, easier. Okay, right now, substitution reaction with chlorine Cl2 with bromine Br2. They'll ask you nitration. That means you're going to use nitric acid, as I said. Okay. And Friedrich's alkylation, alkyl groups, you're going to add in the CH. This alkyl group means I'm going to add in R group. Add in CH3 inside. You can add in C2H5. You can add in something like this also. Okay. Remember, what is a CH3? CH2, sorry. And going to something here. Here is CH, CH3. Whatever group, as long as an alkyl group, you can add it in. Well, substitute inside. Inside group will be your is it right? The whole picture of it. Your CH3, C double bond O, and then substitute inside. Okay, now take a look at all these reactions here. There are 5 of them. Okay, now the first one. First one is your formation of chlorobenzene. Okay, here, right? Now you need to know the equation. Look at here. 6, of course, you can write in this molecular formula, or you can write it in the ring formula. That is in exams. Okay, this is your and plus your Cl2. Now these are the conditions: FeCl3 or Fe iron solid plus must have Cl2 gas here, because this will like to give you right FeCl3. Skeletal formula, this one, but you must have heat, because this must give you your FeCl3. Remember one thing, one year it came out, they asked you for why iron metal FeCl2 and FeCl3. It has very low melting point. You can check in Google later, it's low melting point. This high, over 1,000, is about 1,000 to 2,000. I think you can check it out. It's about 1,050. So it's also very high melting point. Why this is very low? Because this filler here is a covalent substance. Very important. Okay, because of the difference in electronegativity, you can see later. Okay, so FeCl3 is like that. Fe. Okay, we draw the cross and dots. It's like this. Okay, it's a covalent substance. So there's lacking 2 electrons here to form an octet, and this make it a halogen carrier. Okay, now I'm going to explain this now here. Now there are 2 ways to make, but must get FeCl3. Okay, so Fe is 3 plus here, right? You can use directly as the catalyst, or you can generate it from iron plus Cl2. So what happens is here, you can see here, I will draw the cross and dots. So Fe, right? So Cl, and Cl here. Now if I were to draw, use a different color, okay, for iron, dot, okay, and for chlorine we use yellow, okay, cross here, okay, of course it's cross here, okay, you can okay. So for now, plus, I go back to the color, Cl, okay, so it's dot, cross. So what happens is that this filler here, because it's lacking 2 electrons, a pair here. So this is being pulled. This is an electron acceptor. Electron acceptor. Or they call it an oxidizing agent. Okay? Or the newer term you will see that is called Lewis acid. Lewis acid is an electron acceptor. So it will accept, okay, here. We'll go into here. Okay. Now, and if when it goes to here, the Fe will form. Okay, I'm going to draw well, to show the different. Okay, so here, let's see. Okay, the blue color, right? Or different blue. Okay, remember the dot here, okay? But the chlorine will be okay, cross here. Okay? There's chlorine here, there's chlorine here. Right? So now here, if you look at the black color, so if here it accepts the 2 electrons, so you here and here. Plus here will be this chlorine here, right? This chlorine here, this chlorine. Remember now, this pair goes here. Now this pair will go towards chlorine. See how I draw the arrow now? This is called curly arrows. Okay, so go here, and so you get your. So this chlorine will have dot, 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 and dot across. This fellow, this electron here belongs to this guy. Yeah. So now this guy has lost one electron, so you get the Cl here. Cross, 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 cross. It has lost one electron. That's why this is charged positive. The positive sign tells you that means that this is lacking one. It has lost one electron. This is lacking electrons. It will look for electrons. That's why it makes it what I call. This is called any positive here. Lacking, it becomes lacking electrons. Or deficient electrons. They will look for electrons. And where to find electrons? The benzene ring. But the benzene ring here is, remember not, the electrons here are stabilized. They won't react. So you need a very strong, what you call this is called electrophile. Electrophile. Okay, electro means electron. Fire. Fire means light. Love. Okay. So it's called electrophile. So you look for this here. So now this, of course, FeCl4 becomes negative. Why negative? Why negative? Well, it has gained electrons from here. It has gained one electron. This one here. Remember, this is the covalent bond. So this electron is being held back by chlorine as well. Right? So then this is being taken into your iron. So it's less than one negative. So now we begin. Now, of course, this equation will be asked. This whole equation is an draw from here, okay? This one. Okay. I want to show you the color. Now, as I said, this, okay, this fella here, right? Carbon here, all is carbon here. Remember, this Cl plus here, right, has lost one electron here. So it's got cross, 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 cross. So here, remember, chlorine is supposed to have 7, is it? Right? Group 7. So it's looking for electrons. Now, this fellow here, the carbon. I'm going to draw the carbon now. Carbon here, carbon here, carbon here, carbon, carbon, carbon. Okay? Now, this has got only one hydrogen here. I'm just going to draw it up here. So you can actually see the whole mechanism. They will ask you on the whole mechanism. They will ask you for the structure of this thing called the intermediate. So they're going to be very detailed. I'm going to draw also all the electrons here. Now, this is a dot, dot. Now, I'm going to draw here the double bond. We assume it's a Herculean structure. Double bond here, double bond here, double bond here. Okay, now the 3 double bonds here. Okay, now, okay. So we assume something because it's easier to explain. So here's dot, dot, and dot. Okay, now these are all this carbon. The other one is cross, 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 and cross here. Okay, this will be cross, 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 cross. Okay, 4. I'm going to give a different okay. I'm going to give a different color for the hydrogen. Okay, blue color. So it's going to be a dot, dot, dot here. Okay, forgot here. I need to draw the positive for this one. Okay, here's positive. This will be dot, 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 and dot. Okay, right? This hydrogen here. So now this is the actual electron arrangement for benzene. What happens there? Very important now. Look carefully. Look carefully. They will ask you for all this nonsense, all this diagram. Now, this pair of electrons, this pair, okay, so this pair is the pi pair, okay, not the sigma. Sigma is very strong. These electrons will attack. Where you draw is very important. It's from the ring here, okay, from the double bond here, okay. It will go in and attack, and the two electrons will form a bond with this one here. So here, this carbon here, if you draw a whole thing, okay, this is the carbon here, carbon here, carbon here, carbon here, carbon here, carbon here. Okay, this is hydrogen. Let's try hydrogen as well. Okay, hydrogen, hydrogen. Now they will attack here. Now this carbon here will form. Okay, now originally, so it's a dot, dot, dot. Now this, all these dots belong to this first carbon here. Okay, that's called carbon number 1. Okay, this carbon number 1. Okay, now the cross here, this carbon here will be moved to here. It means this will be the cross. It belongs to here. Now the cross here. Draw the cross here. The cross here. Now, I better change this to another color. Okay, let's call this dot. Okay, so now this chlorine here we have 6 dots. Now, okay, positive sign now. This fella here has formed a bond here. So now for the carbon, this carbon here, we have carbon here, right? We have now the original one of the dot. The double still remain, double still remain. Okay, dot, dot, dot. See now, okay? And this will be your cross here. So now this carbon, the 4, but this carbon has got only how many? 1, 2, 3. See now, 1, 2, 3. It's this bond here, but this one, 1, 2, 3. This, of course, is your bond. So this carbon, we have lost it 1 electron. So this carbon here is positive sign. See now? It's lost electron. Why? This electron belongs to this carbon. So the positive sign is formed in the ring. But then the ring, the electrons can move on. No, okay, I'm going to draw for you. Okay, how we call it resonating. That's why it's called resonating. Okay, or localize. I'm going to draw it in this way. I'm going to draw here, okay? Here, so it's easier to compare. Right? Well, the carbon here, carbon 1 is here, carbon is here, carbon is here, benzene ring. Okay, now we attack the top carbon there, so we H here, and the Cl here. The Cl can be anywhere up to you, all right? So we have so far 1 H here, 1 H here, 1 H here, okay, 1 H here. All they remain the same. The first thing is actually it's adding inside here. So remember this is the positive sign is here. What happens is now this pair electron, I'm going to put a cross here, cross here, and cross here. Okay? So 1, 2, 3, 4. So this carbon is 4. So it's okay here. So what happens is this this pair, okay, the pi pair will resonate, will move up here. See? Go up here. As it moves up here, this is a form of double bond, isn't it? So this electron comes to take the place of come here, the place has lost from here. So here the electron will move from here. So I've got now a cross here, which belongs to this carbon. And cross here, original carbon, okay? Yeah. So this carbon has lost. That means if this happens here, the electron here will neutralize the positive here. So now in this case here, this will be the red band, red color. This will be this original electron, the 4 electrons here. But now this carbon would have how many electrons now? Original X, X, X. It's lost 1 electron there to here. Right? This is the original electron here. So now this carbon has the positive sign here. Got it? Okay. So the positive sign has been moved from, if you call it the first carbon, the second carbon, the third carbon, and the fourth carbon. It has moved from the second to where? To the fourth carbon now. Okay. So it's traveling down. Now, of course, the other one, of course, is this one here. The red so you can see. So now this parent can also move down here. As it moves down here, what will happen? What structure you get? Of course, you get this final structure here. Okay. This one here. This remains the same. This going here. Okay. So it's moved anchor positive signs. Okay. So now this becomes here. So the positive sign has moved from 2 to 4 to 6. So how do you represent this? This here. Okay, so here. Or I can draw like that. So this is what is seen in all your answer scheme. But I must draw some first. The H here and the CL here. And a smile. From second to 6 carbon. Second to the 6 carbon smile. The marking scheme here, see the positive sign here must extend to more than half of the ring. So put a positive sign. The smiley Joe. So this is called the intermediate. Very important. They will ask you on this structure. Okay, ask you on this structure. Let me just show you the question on the intermediate acid for structure. Page 413. Right? Now here you can see. I know this your data. Never mind. Remember now, this is a smiley jaw. See the smiley jaw here. See the smiley jaw here. The ring inside here must extend from the second carbon here. Here's where they say the bottom part here. Origin is only one H here. Right? Smile like that. Okay? This is the intermediate. They tell you. Now we want to go to the first part here. Now this is what I want you to look at. For 3 marks, 3 beautiful marks. It's how the structure and bonding, even put it in black. Okay? Structure and bonding of the 6-membered ring in the intermediate T differs from methyl benzene. That means to say that, well, methyl benzene is like this. Methyl benzene. Okay? And the intermediate, of course, is CH3 here. And of course, then there's the smiley jaws in. Okay? H here. And okay, I don't sorry, I don't do here. Smile from here to here. What's the difference between positives here? What's the difference? Ask you for the difference. Okay? So now this is the question. Now it doesn't matter what kind of thing, as long as the intermediate with the positive sign. Okay? So a carbocation or carbon ion. Now look at this here. Now look. Here. So what's the difference between benzene? Sorry here. The first difference, because you notice that is all the if it's methyl benzene or it's a ring here, right? Methyl benzene, all the 6 carbon here is sp1. Here is all sp2. All the 6 carbon sp2. That's not. And all number 1. Number 2. All the angles here, all the angles, how much? 120. All the angles are 120. Yes, sir. Now, for this case here, only 5 of the carbons are sp2. One carbon is what? This carbon is what? 4 single bonds must be sp3. All these angles is what? Here be 120. But this angle is how much? 109.5. Yeah. Now the difference also, the other one, the 3 points or 4 points here. Now here, right? All the 6 electrons of the pi electrons here are delocalized. Right? All the 6, all this one, of course, with the three double bonds. But here only 2. Here only 2 of 4 pi electrons delocalized. Okay. So now I'll show you the marking scheme, okay? Okay, now this marking scheme. See, any three this one here. Right? Bonds, electrons are partially delocalized in T and partially, not completely. Whereas for here, the delocalized system exists only for 5 carbons. For your benzene or your benzene, 6 carbons. Okay, 5 carbons. That's the first point. Second one, 4 pi electrons are delocalized, which is true. For benzene or benzene, okay, or more than, okay, has 2 more. That means all the 6 pi electrons are being delocalized. Okay. The third point is for your T, for intermediate T, one of the carbon is sp3 hybridized. But for your benzene or benzene, all the carbons are sp2. Okay. The fourth point, the angle. Okay, one carbon has got 109.5 tetrahedral. The other, okay, the bond strength for the benzene is the same. Whereas all the others, right, for the benzene, all the angles are 120. You see that? Okay. They will ask you for the intermediate. Got it? Okay, now I talked about this already. Alright. Go back and look at itself. Now, last bit, of course, is they ask you why is FeCl3? Why is FeCl3 a catalyst? Quite a common question. Okay, why is this a catalyst? Because this fellow here, this is ionic already, okay? This is actually called a complex ion, right? The H plus which comes up, see, oh, sorry. The last point is which is very important, is that this one here, remember this hydrogen here, right? This is a cross here, okay? What happens that this electron from hydrogen here moves down. Remember that? Now see the arrow moves down. The electrons here will neutralize the positive side here to give it a ring back. It means it goes from sp3 back to sp2 again. So the H comes out as a H plus. So X see, this is how your group is from. And the last part is H plus this one FeCl is 4 minus, give back your catalyst. So why is it catalyst? Because it's being regenerated. So Fe3 plus is what is being what? Regenerated is the word they use. Okay, that's why it's a catalyst. A catalyst will participate in the reaction, but in the end, it remains the same as the beginning. Okay. Now, in this case here, before I go on to show you a question, this is called continued reaction. Okay. You see later the position where the protein entered. Okay, I'll tell you first is this point here is otro and para. this one here. I told you before, this carbon is called the first carbon, okay? The reference carbon. Okay, so reference to this one, now this is like the first wife. Okay. Okay, second wife can go in. But this the first wife here will direct which room she will stay in. Okay, so it's chlorine, it will go to auto, which is auto here, auto is a called auto in the para position. So I say auto. I want you to do for your homework. Okay, draw for me the whole mechanism for this to this to your auto. This is called 1,2 dichloro. This is called 1,2 dichloro. What? Benzene. Or it's called auto. Auto dichlorobenzene. Same. You know where to put the position. Of course, a 1, 3. Either this or from here to here. Okay? Right? Now, draw for me the whole mechanism, which is from here, from beginning until now. I'll show you how the question come out and how they actually give it the marks. Alright? Question mechanism. Okay, 4, 1, 1. 1. So, alright, see here. Mistaken. Oh, 4, 2. Okay, here, sorry. Alright, here. Polar benzene can be prepared from benzene as shown. Okay. Ask very stupidly, Br2 and Cl2 as same question. So you can Br2 can use see now that this thing see you can use AlBr3 which is also covalent, remember now? Okay. Remember in your AS you got AlF3, AlCl3 and AlBr3. So this is ionic, remember now? Okay. Why? Because of very large difference in electronegativity. This is covalent. That's why you can. Okay. This is also covalent. These two can act as what I call a halogen carrier. They call it in books halogen carrier. Halogen carrier. That means they carry away. Carrier. They can carry away the Br. You can use that, or you can use Fe. Br3, okay, because bromine just use Br, okay. You can use FeCl3 as the spectra. Okay. So of course here it's not very good. They should give you the balance equation. Okay. Of course this is called a scheme. A scheme don't be balanced, but you put a positive here and Br2 here. Then you should have a HBr here. 1 year they gave this one for 1 mark. So you must be careful. Mechanism of course is what electrophilic substitution. Now they ask you to draw the mechanism of this reaction. Include curly arrows. This is very important. Curly arrows, how the Earth move. And any dipoles. Dipoles mean what? Delta positive and delta negative. And charges means a positive or negative. So now for 4 marks, which is worth it. Let's see the marking scheme, okay? Mark is given for how you get your Br positive, first mark. So the mechanism must include the formation of the Br positive, which is here. Okay, now this fellow here, which is a bit bigger here, Br positive. Why? Because it's got only 6 electrons on the cosmos shell. It's what is it called? Electrophile. Loving electrons because it's deficient. So now the next thing is, remember, now the curly arrows must be from here. So the charges, see now, okay, see positive, negative, the mark is good for this one here. Okay, now the movement is very important. It must be from inside the ring here. Okay, you put from outside here, no mark. Wow. Inside the ring, go to the positive here. Okay, right, to form the intermediate. Now the intermediate, see now, okay, the localized positive charge must have 1.5. Of course, last one is from here. Cannot be from here. You put from here, wrong. Salah. Okay, no marks. Kosong. Must say from here. Went to here. Full arrow. Okay, right? To form back some H plus. So see, the marking say 1 mark is for this equation, the formation of your electrophile. Second mark, see 1 mark is curly arrows from the ring. Okay, from the ring, baby, from the ring to Br minus, so Br plus. Okay, then the correct intermediate. One year they say the thing must put 1.5. Okay, I think I'll show you that. Okay, then the last one is curly arrow from here to here. One time also they give you the mark for this filler here. So it depends on the marking scheme. Okay, so this is how it comes out. Okay, chlorine, bromine, same idea. Let's go back to. Okay, see, right? This is how it comes out. Now let's go back to. Here, don't know why the thing is not fine. Okay, remember? So you can go back and now this of course is a famous, this one comes up course, nitration. I'll give you the questions afterwards, you can try it. Okay? Now in nitration, we are supposed to form this thing called a nitrobenzene. Now this is called nitrobenzene. Okay? Nitrobenzene. This is the beginning to making your TNT, trinitro. They call it trinitrotoluene. Okay, TNT. T. Okay, it's actually toluene means a CH3 of the beta benzene. So you can use petrol and make. Now there are other ways to form yourself. Okay, this one here, this is TNT. Okay, you can this is your TNT, trinitro 3. Toluene is on here. So how you begin, of course, with benzene. For your, I told you benzene and beta benzene that can be found in the petrol these days. Go and check the sign there, go to Caltex or SO or whatever. You can check the RON 95, whatever, right? It contains benzene and beta benzene basically, and that's why they are quite carcinogenic. Just be careful. Now you need to know the equation. This is the equation again. Okay? And the conditions. Concentrated nitric acid and concentrated sulfuric acid. This one here, the concentrated sulfuric acid, here is a catalyst. Again, I'll show you why. The conditions also important, 55. Okay, now I'm going to show you here why they come up all the time. I'll just show you one example. So, it's page 7, page 13. See here. Okay, here. Benzene can be converted to nitrobenzene by nitration. Nitration. If it's chlorine, Cl2 and Br2, they call it halogenation, chlorination, or bromination. So it's nitration from here to here, right? State the reagents and conditions necessary to carry out this reaction. See now, okay? Very simple. 2 marks. I don't have here. 0. Okay, I'll show you later. So this will be 55. Normally it's 55. Some books put 60. You want 55 degrees centigrade, concentrated sulfuric acid and concentrated nitric acid. I think I've got something here. No, this is this whole thing. So now they ask you for this 3 marks. No, so easy, right? Concentrated, it should be what? Concentrated. So 2 things: concentrated HNO3, concentrated what? H2SO4, and the temperature must be what? 55 degrees. Memorize it. Centigrade. Okay. 3 points, 2 marks. 2 point, 1 mark. 1 point, 0 marks. Standard one. What direction is this? Very simple. Electrophilic substitution. So simple. Of course, simple if you know lah. If you're an idiot, don't say you don't know lah. Memorize. Substitution. So is it 3 marks? So simple here. Direction process via 2 steps. Okay, blah blah blah. Now, this whole thing asks you so simple, no? Okay, now first here, later going to this game, it says the right equation to show how X is produced. X positive, of course, is what? Is NO2 positive. You see, how do you recognize it? Very simple. I want to put NO2 inside here. It must, there must be NO2 that will attack, you know. The positive sign must be on the end, you know, to attack the hydrogen. So how do I produce an NO2 positive? That is what they ask you here for this question. Let's look back. Okay, I put 6 equals 7. Quite stupid. Okay, see, now this is the equation. There are 2 equations, HNO3 plus 2H4. This is the commonest one. Okay, you can also HNO4, HNO3 plus only 1 here. I'll show you. Okay, but the whole thing is to produce the NO2 positive. Came from your nitric acid. So you get H3O positive and 2H4. I'll show you the other one. Okay, I think it's here. Okay, see, now this is the commonest one. Okay, 2 H2SO4. There's also one. There's also one here and one. See now. See now. Right, now this is 1 H2SO4. See now. Okay, but give it different. You water here and always give you an NO2. The common one, of course, is having an NO2. Okay. So this is important. This is what file? Electrophile, right? Both of them. So the balance equation is 1 mark. 1 mark. This or this. So, but you must get all correct. Balance and all the species correct. Okay. Now, how does it go? Very simple. Now, the mechanism here they give you. Okay. Now, let's go back to same old things. You know, the attack must be from where? From here. From the from here goes to here. From the intermediate. Remember? Right? The H is originally H. This position, okay? You can attack any position you like. Okay? Fire from here to here now, okay? Right? And of course the arrow from here to here go down. To give you a H plus. Okay, lastly, of course, the H plus the HSO4 minus to give you back the H. Catalyst. See now. Okay. Now you can see that I got 2 questions here to actually help you to see. Okay, 55. Okay. 6. Alright. Alright, this question here is question 5. Okay. Part B. When treated with concentrated HNO3 and HNO4, see now, they give you the 2 things there. Okay, the reagents and the conditions. Actually, the condition is concentrated. Okay, right? 2 things here. Okay, this is your reagents. concentrated, and your 5 is called the conditions. Okay, benzene produces nitrobenzene. It's very important if you would write down the equation C6H6 benzene plus HNO3NO. Because from here you can put down here concentrated, and put a concentrated. Now see here guys, you have to learn this. Copy exactly the whole thing again and again until you get in your bloody head. Okay, now for you bloody lazy cows. Okay, okay, put here. Okay, to get you your of course C6H5 and NO2 plus of course what happens is what? What comes out? One H comes from here on, and one O there. One H there, so become H2O. See now. So balance it. It's called a nitrobenzene. So this thing here, equation. Of course, the mark you don't have, but sometimes they will ask you to write the equation. You don't know, then you get. Here, of course, it's called continue to put down there. Okay. What it was a balance equation. Okay. Now mechanism. Same thing here. Outline the mechanism for this reaction. You should include all charges and use curly arrows to represent the movement of electron pairs. Here, did you say charges and yeah. Okay. Now let's look at the marking scheme. Okay, it's the equation here. It's 11 measure 41. Now, 2 marks, 3 marks. Okay, first of course is the 1 mark given for the production. Always the production of the electrophile is an electrophile. Again, you don't know I knock your bloody head out. Here, remember, movement, see now. Curly arrow from the ring. See now. These are from the ring. Inside the ring here. And CH bond. Here 2 together you got 1 mark. Last time here's 1 mark, 1 mark, right? The one has 2 marks there. Now 1 mark. Marking seem all differ because it's 2 mark. This is a 2 mark question, not a 3 mark question. And correct intermediate is not here. See now, the ring here. Right? Now here, see correct intermediate including charge in the right places, that means the charge center. Note, charge area must be more than half the ring. Open your eyes, you blind cows or whatever. See half the ring. Only this carbon here is your sp3. Very important. All the others here is sp2. Very important. Yeah, no? Okay, so that is what electrophilic substitution is all about. Okay, now for the last question, I try to do now. See, I would talk about. See, they come up this. The last one, of course, is Friedel crafts. Friedel crafts contain 2. Okay, 2 sort of reactions here. One, of course, is alkylation. One is what? One is acylation. Okay, I'm going to draw. Okay, see, now here I cut and paste on, don't know where I just type this guy. Okay. See, I want to put an R into here. See now, in books they still draw the curve structure because it's easier to draw. Okay? Easier, but it doesn't matter, right? But basically in CIE they would like to have the resonance structure. So follow CIE. All right. Now, very simple. This is alkylation. See now, okay, alkylation. That means I want to. Because now this is a bit hard. Doesn't matter. See, I want to make from here to here. Okay. Now, if you look at it, this is the final product. I want to make this here. Okay. Now, you must understand this here, this is your original carbon. So you don't understand when you write out, you draw all the carbons. Don't be so clever, as if you're so clever, but you're not. Okay, all the carbons here. You still don't know that this is the hydrogen. Okay, all right. Draw for yourself. So you know. The skeletal diagram can be a bit confusing, and then you assume you know, but actually you don't know. A fool thinks he knows, but actually he doesn't know. Okay, C6H6. Now, remember from here to here, they put this carbon, this is carbon number 1. This is carbon number 1 here. Doesn't matter what you call it, it's all the same because it's symmetrical. Okay, now this carbon here. What I've substituted here is a skeleton. This is a C here. You don't know, say don't know. Let's say put CH3. Okay, this is a H here, and this is a H here. That's not. So I'm going to substitute my hydrogen for a CH2, CH3. This is your CH2 dash CH3. That's not. 3 here. So what I do? Very simple, right? I need an alkyl halide, halogen alkane to go inside, and I need to remove the chlorine or the bromine. So here I start with, of course, I start with a Br or a Cl or an iodine. See now, fluorine is a bit too strong, so normally they use either and I use a halogen carrier. If it's Br here, I put FeBr3. I can also use AlBr3 or AlCl3 or AlBr3. Anyone, these are called halogen carrier. They will carry away the chlorine. Now here they give it like this. Now I show you another way, which is here is more easy. Here they put all this stupid here, but you don't need to be so detailed. What happens is that here, you can see now here, right? Now of course this here is, you can draw it up here. You want to Cl, here is Cl. So you have dot. Remember AlCl3 is covalent, As. So there's an empty space here. This of course is carbon. It's the alkyl group. First here is a 3. Okay. So here's this is your cross. Okay, right? Cross. And there's a dot here. This is how your dots here. Chlorine originally got 7. What happens is that this pair, any pair will do from here or here, goes to here. This is a halogen carrier. This is a Lewis big acid. To accept the low the pair acid to become Al, what? Cl. Now this will form what kind of bonds here? Native bond. Okay, so it's dot, and then this pair will attract towards your chlorine here to form dot and a cross. This fellow is whose electron is a carbon electron. So this will become a negative sign. See, and of course this you form your alkyl group now. In this case is this one now. Positive carbon. This now become the what? 5 electrophile. That will start the okay. In your nitration, it will be your NO2 positive. In your chlorination, it's Cl positive. Your bromination, Br positive. In your alkylation, is R positive. It's right here. See now? Yeah. Okay. So now this positive sign here now will the same thing. Here is better. Okay, it's bad boy. I say from here. Can be from here as well to you, like this method. Okay. Normally in Cambridge, you want to so from the ring. Okay, Okay, attach here. So here, if you cannot see like this one here, draw all the CH3. CH3. So now the hydrogen here, of course, here there's an original hydrogen, which is here. Okay, so this is your intermediate. So you smile from here to here. Right? So put a positive sign. Okay, right? So now this 2 electron here will move down from here to inside the ring. Okay, this is not very good diagram. Okay, move inside the ring. Okay, so this electron here will neutralize the positive sign here, and of course it comes with the H plus. Okay, so the H plus comes up. Forget the slow and fast. The H plus, of course, will plus your Al. Now this is 1 mark. Cl4 negative 4 mark. Al, Cl1, 3 plus HCl. This is 1 mark. This is your catalyst. It's being reformed again. See? This is your halogenation. Your alkylation. See? So in this case here, same as it. Now, of course, in this case here, right? You can see the steps. Now, this is not very good, okay? I mean, place to join this one. But you can see here, right? Alkylation, see now? Okay? This is the equation. Okay? The Cl, if you Cl here, see, I want to substitute a CH3 here. So I need a CH3 plus halogen. See now? Okay? So this being carried away by here. So the first part, of course, is your production of this methyl carbonium ion. Carbon ion. So the tech from here. Here. So this is the whole thing. Right? Just let me show you a reaction. Okay, there's a question. Okay, quickly. 403. 403. There's a question. There are 3 questions actually. Okay. You must see very carefully now from here to here. Alright, see here. The anti-inflammatory drug ibuprofen. Ibuprofen is just almost like the Panadol. Can be synthesized from that bromine from the following blah blah blah. Now from here to here, look carefully. From here, this what is this? It's a benzene. You must open your bloody eyes, okay? C6H6. Here. This is your skeletal diagram. You must know what this whole thing is about. You don't even die at it. It's a C. It's a C. C. CH3. It's a CH3. It's a C to how many H? 1 H. Okay, draw it out. You don't know, draw it out, please. Don't assume you know and you don't know. Okay. So now this whole thing here is being substituted with a hydrogen here. This one here, you draw here. You can draw anywhere. Okay now. So what we step 1, they ask you for suggest the reagents and conditions. Simple as that. You have to now figure it out. So what will be the reagent for this? I know that I must produce, which means in this case here, this one here for the attack the ring, it must be the C positive here. That's going to join the ring, isn't it? Thing is a brilliant thing. Please, to H here, the H here, and to the C here, draw backwards. Okay, here to H here, hit to what? CH3, hit to what? CH3, isn't it? Yes, not. Yeah. And of course, to go backwards here, it must be CH3. So use your brains. A levels, not B levels, not I level, idiot, or not E levels. Okay, to a Cl, say, plus what? Plus, of course, FeCl3. It can be Br, it can be iodine, or of course, you put the relevant one, okay, don't be idiot, okay, or AlCl3. Anyone will do. And of course, heat. They didn't ask you for whatever. Heat normally is the one that you require. So here, okay, reagents for condition 1 to 6 cannot. Okay. Now here, go and think. This step 3 is AS. Let me tell you first. AS. Tell me. Okay? This part here. Now the other one, you're going to substitute the other one here. Tell me what kind of substance this is. Okay? This substance, now remember this is a C, CH3. Right? The rest of this comes from original here. So I'm going to substitute my hydrogen from here. Okay. Yeah. Now, what substance is this? Who can tell me? Of course, you cannot tell me now. Okay. If you can, fantastic. I'll give you 2 seconds. One, of course, it's cyanohydrin. You have to know. That's why it's called A levels, not D levels, okay? Cyanohydrins. Cyanohydrin. How do you make a cyanohydrin? This must be a what? A ketone, is it? Or the aldehyde, is it? Right? So it must be a double bond here. That means this fellow here must be what? Must be like that. So you need to go back and try again. Okay, my beloved students. Don't assume you know. Look at me. No, don't know. You don't know. I think I can reproduce it. Must be a C here, right? CH3 here, and what? It must be a double bond. Yeah. Now this is the second part. How do I attach this group inside here? Now this is called acyl group. Remember now? Acyl. Right? Now we come to the last one. Okay. How do you acylate? Acylation, okay? Put this inside here. Kick out the hydrogen, put the acyl group here. Okay, let's go back to our notes. The same old thing. Okay, all right. Now, all the things here, this very nice. I bought this thanks to Gloria. Actually, she encouraged me to suggest to me. She encouraged me to suggest to me actually to buy Rion, which is very good, so I can dish out live, you know. Okay, so now here, see, introduce here. This become a ketone, you know. Right? Why is it ketone? I hope you know, C, R, double bond, O, and R, you know, yeah. So this is R group here. Okay. Okay. Now, how do you introduce these groups inside here? That means I must get this one here as your positive, is it? And not positive sign here. So I need to chlorine, I need to kick out chlorine. Normally Cl halogen is need to be kicked out because why they are charged, they are partially charged. Okay. So this one, this is called acyl chloride, okay? The name is called acyl chloride. Or ethanoyl chloride. 2 carbon ethanoyl. Okay, now. So of course this one here is like that CH3, C double bond O, and your Cl. Because I need a halogen carrier. Now for most Friedel-Crafts reaction, let me just tell you this, okay? You will find that in your marking scheme. For Friedel-Crafts, it means for acylation or alkylation. They normally use AlCl3. Normally. It's not wrong to use FeCl3. It's not wrong. But normally, marking scheme always is AlCl3. Okay? To kick out, to remove, to carry away the chlorine. See now? Okay? I can see here, I got cut and paste, you can see, okay, now here. iron as well, right? Okay, remember this, so dot, 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 cross, cross. See, very nice at this here. So fine you can draw. Yeah. So now this is, see how covalent is. So they form a dative bond. So the pair here will move towards here. Okay? Dative. And 2 electrons here will move towards here. So okay, so this is one now dot. 3 only. This is positive sign. Ah, this one attack now. See from the ring.